My name is Mike Kraus. I'm from HPE. I've been working on Gen Z technology from its start. This is something that's a culmination for me, about 6 years worth of work. So today's talk is going to talk about Gen Z as a whole. It's going to give you an overview of the technology, and toward the end, hopefully you'll see how this can apply to in-memory solutions. And in fact, I show some data at the end about how using this in in-memory applications does a dramatic speed up in application performance. Let's see. Why are we going down? So Gen Z was motivated by a whole series of hardware-centric things, and I believe most people here are probably software-focused to a large extent. But at the end of the day, what we really ran into is one of Patterson's three walls, which is the memory wall. How do we improve access to data? How do we improve the latency, the bandwidth, the ability to do various types of services on that data, and do it in many times in a more secure and robust manner than before? Obviously, there's a lot of data going on, IoT, everybody can talk about all the things that are big data focused these days. But the bottom line is still we have a lot of data to crunch, and we can't, in our view, continue to do it with the same technologies we've been doing for the last 20 years. So if you look at the traditional buses that are out there, you've got DDR for memory, you've got PCIe for I/O, and then depending on the fabric and the storage technologies, you could have SAS, SATA, fiber channel, Ethernet, InfiniBand, et cetera. So there's lots of ways to do things, but one of the things they all suffer from is they've been designed really with an eye on data is very far away. With the exception of DDR, data is generally viewed as far away. So there's a lot of software overheads involved in it. There's a lot of complexity. What we try to do with Gen Z is say, let's simplify it. And I'm going to skip through a couple of these slides just because they're more proof points about how things are going bad. So we also have this view where we're getting to new medias that are out there. We've got new types of storage class memory medias, 3D crosspoint, spin transfer torque, ReRAM, you name it. There's half dozen or more out there competing for it. We've also got a future of new generations of flash media coming out. Very high capacity, very high bandwidth in many cases, as well as lower latency flash coming along. So when we look at this, we start seeing how do we stage our memory. So years ago, I gave this example to someone the other day. If you look at the old TPMC type benchmark, years ago, you'd build a $30 million system to get to 1 million TPMC. Of that 30 million, 29 million was nothing but storage arrays. Today, we've collapsed that down significantly. We've gotten rid of the rotating drives, we put it all in solid state drives, and now we've seen a huge increase in performance. That still isn't enough. When you look at the amount of data we have to crunch, we have to start thinking about how do we move to more load store access. And today's block access, which is great for lots of things, moves a tremendous amount of data back and forth in order to just access a small quantity. Even DDR is incredibly inefficient in this regard. A single 64-byte read or write on the memory bus can involve 10, 20 kilobytes of actual data movement because of interleave and the way we fetch things at the row level within the memory devices themselves. So what we want to do is think about how we can change the way we organize our data, where we stage it, create different tiers of memory, if you will, and try to make it to where we minimize the amount of data we move back and forth in order to improve performance, reduce power consumption. This slide basically says, oops, sorry. Someone gave me some slides that have animation, and I'm not an animation kind of guy. We've got a lot of different interconnects out there, and one of our biggest things that when you actually glue stuff together, and I've been responsible for helping create a lot of these different interconnects, so I can share some of the fault. But part of the problem we run into is we spend a lot of time transforming a piece of data over one bus into another interconnect, and eventually we find our way into some memory media device or into a cache in a processor. That's actually spending a lot of time just transforming stuff that only existed because we thought data was far away. So the reason block semantics is we had rotating media, so we had to create all sorts of stuff to keep the processor doing something else busy while we were waiting for that rotating media. Even with flash, today's flash is 100 to 300 microseconds away. processors have a lot of spare cycles if they were waiting for that to happen. So we end up spending a lot of time figuring out how to organize our flash drives, bring our data into the main memory, and then we spend a lot of time moving back and forth. We'd like to say, can we eliminate those translations? Can we move to more of a memory semantic world, more of a load store semantic, and only move the data that needs to be moved? If we look at the way we've tried to do some of that with SCM, the traditional approaches right now are to use the DDR bus or the PCIe bus. And each bus has its pros and cons, but there are a lot of issues with it. Number one, if you think about SCM, you're telling a customer, I'm going to put like a terabyte of data on a DIMM, or a terabyte or more of memory on a PCIe chem form factor or such. And that has one interface in and out. So if that customer has lots of critical data on it, and that system fails, you've lost access to that data. And unless you want to provision a lot of memory plus I/O bandwidth to replicate that data constantly, you're always going to be at a loss at some point. So what do we want to do? There's a lot of things. We want to get high performance, reliability, security, flexibility, composability. We need to be compatible. We need to be open and available for anybody to access. So this is where Gen Z comes in. So Gen Z is an open interconnect standard. It actually was public a year ago this month, a little bit earlier than this day. It allows you to attach any type of component to any type of other component. It could be memory, I/O, FPGA, GPGPU, DSP, you name it, you can attach it. It can be done in a point-to-point topology within a co-packaged solution, within a single enclosure, within a rack scale. So you can actually do this stuff at various levels of scalability, various levels of composability. You can mix and match media. We abstract the actual memory media itself so that it has a series of attributes, and then software defines how we bring that stuff together, where do we stage things, where do we position them, et cetera. Very quickly, we've got 48 companies at the moment that's been growing. All these companies are able to actually cover a variety of different types of components. So in general, the whole ecosystem is coming together. So what is a memory semantic fabric? One is we try to get it to where we can take load stores from the processor and turn those into operations on the Gen Z topology, whether it's point-to-point, swish, mesh, doesn't matter. It is something that can allow you to use traditional storage semantics, traditional block semantics, traditional load store semantics everywhere. The great thing about load store is you don't have to think about where you place the data. How much data did you have to move? You don't have to stage it. You simply say X equals Y. The data for Y is mapped to some memory address range within a processor. The logic within the processor, the MMU logic, maps that into a Gen Z requester block. The requester block goes out, gets the data, and brings it back. You as a software programmer didn't have to do anything other than set up the mapping, which is no different than what we do today with DRAM or SCM in the future. So this slide basically illustrates that because we can just simply map the memory and load it, instead of being 25,000 instructions in here, and I think people will quibble as to whether that's 10,000, 20,000, but it's typically thousands of instructions depending on whose software stack you're going through. You can replace that with essentially a couple operations at the processor level and you're done. So once you've mapped the memory, you can just read and write it all you want. If your processor supports far atomics, in the sense that you can have the atomic run out in the memory module itself, you can actually execute logic out there as well. So for example, the ARM ISA supports this concept of far atomics. So you can actually now offload certain aspects of the processing out into the memory module. The other things you can do with something like far atomics is you can also say if that memory is shared by multiple entities, you can put mutex equivalents out into the memory itself, so you can do access control through the memory rather than having to coordinate it between the processors and the operating systems themselves. So this means that when we offload this stuff, we also offload a lot of complexity within the processor. Today's processors assume everything must go in and out of the processor because coherency is king and everything must be coherent. The fact is it's going to probably be about 5/9 of the data doesn't need to be accessed coherently. It's a complete waste of time to push it in and out of that coherency domain. So this is why you see a lot of things going on with GPUs, FPGAs, DSPs, et cetera. People are saying, look, I just need to keep coherent what is used for control, things that I care about, locks, things that I care about access, et cetera. But everything else, I can point directly to the memory and say, go over there and process it. Go over there and access it directly. This is what I called, years ago, memory-centric computing, where we eliminated the processor in the main data path. So processor in the path is the processor-centric. We support that. Memory-centric is everybody can get to the data simultaneously if they want. So when we talk about, from a messaging perspective, if you think about today, we have that load store world, but we actually do a lot of stuff in messaging. The reason we use messaging is because it takes a long time to talk to some remote processor. So we end up having to do, program a PCIe NIC, program work requests, DMA down to the NIC, have the NIC transform those into Ethernet frames or InfiniBand frames or OmniPath frames or whatever. Gets to the other NIC, the NIC decodes that, turns it into a bunch of PCI DMA operations. Those get up into the host processor, and then eventually we hit some processor cache or a memory bus to put the data in. So in that, we translated the data several times, and we had to do that because we don't know where the other side is. Well, Gen Z isn't about trying to take on the entire world. It's about rack scale, perhaps, within a data center, but it's not trying to say, let's work anywhere in the world. So if we can do that, we can actually take that memory semantic load store type mentality, combine it with a little offload capability within the processor, and do the same reads and writes that we do to translate loads into reads, writes into stores into writes, and use that to message between our systems. And as a result, we can actually extend and communicate at very high speed and offer differentiation where you have a common fabric, common capabilities, and because of the way we've architected it, you can actually deliver qualities of service and different path selections, et cetera, so you can isolate ultra low latency traffic from low latency traffic from best effort traffic. And so the hardware actually supports a variety of different multi-link type solutions, multi-path solutions. Virtual channels are much, much simpler than what you see in, say, InfiniBand or PCI Express, dramatically simpler than PCI Express. And by the way, I'm responsible for both of those technologies in part. And we're able to do it at much lower latencies. So our switch latencies, 30 to 50 nanoseconds, depending on the switch radix. Your typical switch chip that you see in Ethernet is hundreds of nanoseconds. In InfiniBand, it's about 90. OmniPath's about 100. PCIe is about 120 to 150. So we're doing it at much lower latencies, which means we can do fan out, we can do connectivity without it necessarily causing the processor to have an issue or the workload to have an issue. We support a variety of different routing algorithms. You can actually support pretty much any routing topology there is. You can have adaptive routing or dispersive routing. Adaptive means you're able to react to workload conditions, failure conditions. Dispersive means you can take advantage of all paths as you wish. All of that's software defined. We have dynamic congestion management because eventually anything that's with a switch at some point will have congestion in it. And because we're using a common protocol, we don't suffer any of the protocol translations that I described earlier. So that, in a nutshell, gives you a lot better performance. From a hardware perspective, we have multi-path. This is something that DDR doesn't have, PCIe doesn't have. So we have links. Components can have, in theory, up to 4K interfaces. That was basically at the request of one of the tier ones who wanted unlimited scaling. But we can automatically take advantage of all those paths simultaneously. And if one of those paths fail, you automatically go around it. You don't care. The data itself, actually the error model, the way I designed it, is the transaction that's in flight is the only one that gets hit, only one that has to be retransmitted if you're doing reliable communications. So if you're taking advantage of multiple paths and something happens, and typically in most of the other technologies, they require very strong ordering or they use sequence numbers to keep everything in an order. If a path fails, you have to retransmit the sequence. In something like OmniPath, they actually have it to where you have a bunch of replay logic in each switch hop that tries to retransmit the sequence around and bypass the error. But that comes with a price, the 100 nanosecond type latencies versus 30 or 50. So you have to think about how often will you see errors and certain types of failures compared to putting the complexity in the hardware that you pay all the time. Again, we have multipaths, so you can distribute the traffic. If a path fails somewhere out in the middle of the topology, the fabric, the switches, if you've done them right, will automatically bypass the failed path and select one of the alternatives for all subsequent packets. We do a variety of things from a security in terms of hardware isolation. We have access keys that allow you to restrict which components can talk to each other. This is actually not a huge space. In InfiniBand, we did a 16-bit value. We actually came down and realized that almost all implementations after 18 years of implementation, they do 128, of which you have a full and partial membership, so it's really only 64. So we decided 64 is actually a really good number. Allows you to do a first level hardware filter. We also do region keys, which are basically on a per page basis. You can establish access, permitted at all, read only, read write access. So this allows you to make sure that components, especially once you get into being them shared, can only access the data that they're allowed to access. And one of the things that we have as a philosophy is every component's an attack vector these days. That's something that all the cloud guys and that care a lot about. In addition, the architecture supports cryptographic protection. That's an optional thing. You can put it just on your control plane. You can put it on your control and your data plane. This allows you to do packet data integrity checks to see if someone manipulated a packet and tried to replay it. There's an anti-replay tag option in there that allows you to catch that. There's a couple different techniques that are used. But the main thing here is we want to be able to protect the control plane because more and more enterprises, banks, cloud providers, et cetera, they care a lot about someone redefining their software-defined world and saying who can now access stuff in a way that they shouldn't have. And as Equifax and a bunch of other people have taught, Yahoo, et cetera, have all taught people of late, there's lots of ways for people to corrupt things if you don't put into the hardware especially, the types of protections that you need to keep things isolated. We also, it's not shown on this slide, I added in recently the ability to detect if someone were to quiesce or put an NVDIMM or a memory module asleep and then substitute in one on the fly, be able to detect if that substitution occurred in a fairly reliable manner. So that allows you to intercept, like someone say authorize some keys, you quiesce it, take the guy out that's been authorized, you put something in, that's your rogue actor, we can now detect that at the hardware level. Again, this crowd is more software is what I discern, but basically we built it in the architecture to scale into from 100 gigabit type solutions to terabit and eventually terabyte beyond type solutions in terms of bandwidth. So every link, for example, if we do by 4s, which would be the most common, by 21 time frame, we'll have 400 gigabit type links, very, very common within the industry. Gen Z supports that, and in fact, we started one of the first to go out and talk about 112 right off the bat. We also support the PCI Express PHY. We can scale, again, the number of links because we're not limited to a single link. We can actually scale the number of links up and allow you to operate at lower signaling rates or much lower cost implementation in terms of the hardware itself. So a lot of bandwidth to spare. We also support different loss budgets in order to reduce power consumption and such, which is a big deal within a data center. Every component can be composed depending on how you set it up. If you're in a point-to-point topology, a processor talking to another component, you can put any pairing that you want together. FPGA to processor, processor to processor, ASIC, whatever, it doesn't really matter. But more importantly, you can now attach and compose through a switch any scale of solution that you want, from a single enclosure to a rack scale to many racks of composability. So one of the things that we focused on a lot, and that's where the initial products will be focused, is composable memory I/O and storage. We don't want anything ultimately to be stranded. Our customers, ones I talk to a lot, very, very concerned about data being stranded and lost because the data sets are so huge and so integral to their business operations. Again, we can support lots of different topologies. We can have co-packaged memory, ultimately. At some point, DRAM won't be uniform in its latency, so you'll need to do something like Gen Z. We can do it at a local system, a single enclosure, rack scale, and then you can do it at scale out, like I said. One of the things that we did is we've actually been driving very hard on the mechanical side. Most people probably in this room aren't aware of all the mechanical issues, but if you look at the DIMM, it's a horrible mechanical solution. If you look at the PCIe Chem card, when we wrote that spec in 2000, it was already years old in terms of the mechanical. It's been modernized and such, but we realized it's becoming more and more problematic to continue to use those mechanicals. So we came up with a new connector. We wrote a spec in just a few months. In this case, TE was actually, we had seeded them a lot of requirements years earlier. They actually had a great choice for it. So we've got it to where this connector can be used in just about any environment. And in fact, this connector is now being used or proposed to be used inside of EDSFF, COBO. It's been proposed into JEDEC, the PCI SIG, OCP, et cetera. So there's lots of places that are looking to use this connector. So one of the things we did is we got the spec done very quickly and out there pretty much ahead of everybody. We can support unmodified OSs. This is really critical from a transition perspective. You can run block storage type solutions. You can run storage class memory solutions, and you can do messaging solutions. All the OS sees is normal NVMe drives, for example, if that's what you want to do. They see normal memory that's just mapped in transparently like it's done today. And from a messaging perspective, we do an emulated NIC in software, which is just a variation on a virtual NIC, if you understand that term. You just change the memory mappings and such, and now you're messaging across a fabric. And then from a high-performance compute perspective, we also will provide a libfabric provider library, which will allow you to substitute in under MPI and other workloads completely transparent. One of the things that we did with PCI, and this is really critical, is actually, and I serve on the PCI SIG board of directors, the most valuable thing that PCI has done in these last 25, 30 years has been to standardize a large percentage of the software ecosystem. The problem with PCIe, it has that single point of contact with a device. It can't do multipath, and it's actually fairly limited. It does DMAs really well, and a large percentage of the spec is just managing the PCIe fabric. It's not really about improving the performance of the system. So what we did is we defined these logical PCI devices that give you the software view as though it's a PCI device without any of the limitations. And what that means is we can fully exploit what Gen Z has to offer, number one. We also eliminated all the complexity and cost of doing SR, single root I/O virtualization, multi-root I/O virtualization, et cetera. You can actually share devices transparently, and the software is dramatically simplified. You also get extremely low latency switching in comparison to a PCI, which means from a read perspective, we cut 200, 240 nanoseconds off of every read request just from the switching topology itself. So now you can scale these things with much more confidence. So if you're trying to create large storage pools of SSDs, program them using NVMe, et cetera, all that can be made to transparently work, and yet you'll have natural multipath, natural I/O sharing, natural composability, and recovery from any hardware failures automatically. We also put in all the atomics, so PCIe only has 2. We actually have the atomic capability to support 3 different ISAs as shown. And we support multiple physical layers. So the PCI SIG has announced they're going to go to 32 gig. Most of the country outside of PCIe is already at 25 or higher signaling rates. Gen Z starts off at 25 on the 802.3 electrical. We'll go to 56 and then 112 fairly quickly. But we're supporting both PHYs because there's a lot of pins on processors and such that speak PCIe, and we want to just be able to tap into that existing ecosystem. Like I said, you can enable these and compose them in any way you like fairly easily. And it's not yet public, but there's also something called a logical PCI hierarchy that's be in the final version of the spec. We're about to release the .9, which we're right on the locking down tomorrow, in fact. But we'll make all that public, the final spec, and you'll see these logical PCI hierarchies. And this allows you to actually put native PCIe devices into a Gen Z topology, and that just transparently works. From a memory perspective, we support the traditional memory models. You can put DRAM in, or you can put SCM in. So there's a variety of different types of solutions there. Most memory, to make it work, firmware simply maps it in to what the processor sees as an address range. And once those address ranges are programmed, now you just load store just as before. So the way we set up the MMU logic is such that a certain address range maps to a page, the page maps to a component out on the fabric, whether that's point-to-point or otherwise, and so you just flow through naturally. So the processor, the higher level logic in the processor, completely unchanged. It's only the lower level where you do the which path am I going to go out? Am I going to sequence DDR, or am I going to sequence HBM, or am I going to sequence basically Gen Z? To do that, we had to support these different memory medias, we split the memory controller somewhat. We take the lower half where that sequencing is done, and we call that a media controller. We push the media controller logic over into the memory module itself. That media controller then does all the memory specific media logic. So if you're doing DRAM, you have to refresh, et cetera, it does it. If you want ECC protection, high levels of data integrity, you want to spare things, you want to do row remapping, you want to do chip remapping, et cetera, all those things are completely hidden behind the media controller. And that's where the kind of magic, if you will, lies. So that allows you to then insert value add. So if we talk about data-centric compute, today, if you're doing DDR or HBM and that, you can't insert any compute in. The most you can do is kind of be zero. You can't really do anything more than that because that's the way the buses are designed. With this approach, we can actually integrate embedded processors. So for example, some people have talked about integrating RISC-V embedded processing elements in, and so they could offload and do more pre-processing in the memory subsystem. So there was a talk in the other room this morning where they were talking about processor and memory, and it was interesting. It has a number of interesting elements to it, but it actually it's got a lot of challenges too. I'm not being critical of them, I'm just saying it's harder to do certain things because you have to still bring the data into their particular component and then use the SRAM that they were doing to make that work. Here, we can do completely unmodified memory media components. So if you have a DDR memory media, a flash media, doesn't matter. All of that is just native. The media controller abstracts it and takes on the complexity. It translates the read and write commands into whatever the media-specific commands are. And again, we can scale our memory out. So instead of being limited to a DIMM sitting a few inches away from the processor, we can actually put the memory in the front of the memory enclosure. So one of the things that a lot of people haven't considered is you got that SCM DIMM, so an NVDIMM-P or Intel proprietary or whatever, it's sitting in that DIMM. If something happens to it, you have to open up the box to get it out, put it someplace else. With our new modular form factors that we're doing, and that we can actually put the memory itself into the front and make it serviceable. We also have the option of doing just like a DIMM if you want that ultra low cost locked in capability, but we can make it to where that memory, if it's independently powered, has an alternative path out of the box so it's never stranded. So we've made it to where we can do that. We can now scale it. So now we can mix and match. We can do that kind of memory-centric architecture I was mentioning where everybody can talk to the memory simultaneously. I'm just going to build this out. I hate animation, sorry. But when someone has nice pictures, I like to leverage. You can put the memory pretty much anywhere. So like I said, you can see on the upper left, we can have these composable memory media modules that are fully inserted. Just like you do a storage drive, you can hot plug them dynamically. You can do them as asynchronously managed or managed for the hot plug type services. And again, you can integrate them within the box, and then you can also do them at rack scale. From a block storage perspective, obviously we support today's PCIe links, and that's how everybody does most of the NVMe today. We can just replace those PCIe links, still even using the same PHY, the same pins, and simply make those Gen Z links. So that allows you to get in there fairly quickly. The other thing that you can do that you can't do with PCIe is you can't do multipath. Now you can try to put a non-transparent bridge in, which is basically a non-standard way of saying there's two hosts that can talk to the same component and do some amount of sharing that way, but it's still fairly limited. The PCIe PHY is really within the same enclosure. It comes with some complexities in terms of how far you can drive it and that. But it also comes with the limitations, like how is error handling done, who masters things. Having active-active is very hard in something like a PCIe environment, whereas in Gen Z, it's built into the architecture from the start. You can do simultaneous access. The other thing you can do is you can put these at scale, like I said. If you're doing NVMe, which is not latency sensitive, it's not a load store domain, you can actually have those further away, so you can have rack scale of this without being limited. Today's PCIe, for example, is 256 bus numbers per hierarchy. Most of that is 256 bus numbers. Every component uses a bus number. Because of the way the operating systems operate, maybe you scale to the 60, 50 range for most. Maybe you could get up to 100. There are people that want to do 1,000 drives. Trying to do that with something called flattened portal bridging, which is a new capability in PCIe, is incredibly complex. With Gen Z, you can scale any SoC, you can talk to 8,192 drives, and it'll all look like PCI, all logical. So we kind of break that out. And you can then think, okay, now I've got every SoC can see 8K components just with PCI semantics. You can go a lot bigger with Gen Z. In theory, Gen Z, way we've architected it, allows you to scale to a couple 100 million components if you want. No one's going to build that, but the architecture does support it. The best thing is now you're not limited. You don't need an NVMe over fabrics. Nothing wrong with NVMe over fabrics, but I've heard several people say it's just recreating fiber channel. For a lot of us, we're just like, why don't we just keep it simple? Keep it flat, keep it native. Don't bother with trying to mix different technologies together to compensate for shortcomings in PCIe. And again, nothing wrong with PCIe. Still serve on the board of directors there, still actively involved in creating it. But it was designed for a very specific use case within a single enclosure, not to do these more complex capabilities. And again, we can scale it out. Lots of things you can do. You can also mix and match load store semantics. So some of the storage people we've talked to want to mix kind of a hybrid where they have a certain amount of data they keep in DRAM or embedded DRAM within the storage module, and then the rest is in flash. So they can do load store semantics very fast out of the DRAM and then block semantics out of the flash. And they can, again, as SCM comes about, the DRAM could be also SCM, so they always have persistence. Everything in Gen Z actually supports, every module can support multiple media types, and you can actually have commands that they're actually called sanitize and erase, but it's actually more than just what sanitize and erase are. You can do true sanitize and erase semantics, you can do kind of zeroing out of memory, you can do cryptographic key erasure. There's lots of things that you can do and offload into that in order to accelerate how the storage behaves. From a messaging perspective, like I mentioned before, we can emulate an Ethernet NIC. So you can take the entire virtual NIC software stack that there is, put a little bit of logic addition on that to remap to an alternative node, and that entire ecosystem just ports over. So if you have virtual switches, et cetera, they see an eNIC as though it's a physical NIC, all that ecosystem comes for free. So now you can, instead of being limited to a small number of nodes in a virtual switch environment or a single node, you can actually extend that to any number of nodes, thousands of components if you want. And then Gen Z has been used. These numbers actually here are measured numbers. These are some benchmarks that my company has done, but we've actually put together everything in memory. And by putting in memory and actually running this over Gen Z, you can see we've gotten 15x to 8,000x increase in performance, depending on the workload. And this is just the start. This is only what's been proven in the last year. Some of the changes are already in open source. For example, the Spark changes to do this, we've already contributed back into the Spark ecosystem. Everything we're doing is open from an architecture perspective. Our specs are public, our drafts are public. We try to get everything in the public. So it allows you to talk to pretty much anyone about anything. Everything we're doing is open source. Our firmware will be open source. Everything will just be completely out there. But these are the types of numbers that you can get when you move to everything in memory, and you can do now memory at scale without being forced to buy the highest cost DDR DIMM, for example, really, $10,000 DIMMs. You can replace those with lower cost, lower density DRAM or SCM or flash or mix and match to your heart's content. So I went through that fairly quickly. Questions? Yeah.
So with the way IMC does the array, if you will, it would appear that there won't be too much of a requirement for all flash arrays.
No, actually, it doesn't change anything from a Flash perspective other than make things faster and actually makes Flash more usable. So one of our new mechanicals, and I'll show this at Supercomputing next month, just a couple weeks from now, we can put 48 terabytes into our new mechanical of Flash. And so there's definitely, and that could be PCIe attached, whatever, the mechanicals are protocol agnostic. There's definitely a need for Flash, without doubt. And there would be different types of flashes out there. There'll be low latency, high capacity, just variations on performance and capacity trade-offs. And that's actually one of the biggest issues with SCM media, is most people wonder why it's taking so long and why, in many cases, people are making trade-offs. The saying is pretty much you either get capacity or you get performance, but you don't get both. And so Flash will have its role because it can give you good performance, especially if you can tap into all of it. And it has tremendous low capacity, so it's very low cost per bit. So Flash definitely still has a role to play. Whether it's a Flash array, I think it comes down to how well software-defined storage, intrudes into the array market. But I don't see arrays going away. They serve a very important role within the data center. It just not every app needs every array function or needs to have an array attached to them. Other questions?
When it comes to implementations, how's the adoption?
How are we implementing it?
When it comes to implementation, how's the adoption in the industry?
I'm not following.
How fast people are adopting this?
Oh, so we actually will show, we actually had it at Flash Memory Summit, but there was a fire on the floor. So those demo will be repeated at Supercomputing in a couple weeks. We actually have a dozen companies that are already memory media, processor, et cetera, that'll be demonstrating through FPGAs that are running the protocol natively today, exchanging data, and they'll show different applications working. From a product perspective, the earliest products are 2020. It's mainly a question of at the end of the day, especially on the processor side, you have to intercept a processor schedule. And so we're just kind of off on that schedule. So first implementations will use a discrete bridge attached primarily through a coherency bus off the processor. And then second generations will do integrated, and those are people are already doing those types of architectures. From the media controller side, there are a couple different vendors already showing their concepts and working it out. Their logic is typically 18 months to do an ASIC. So that's why we say once you get the ASICs back and everything else, call it 2 years, products become 2020 because you have to integrate and validate it all. You had a question?
On the hierarchy that you showed near the beginning,
Mm-hmm.
you had something called unpackaged memory, which is above the DRAM.
Yeah, so today you have HBM, high bandwidth memory, which is a TSV-based solution. TSVs are actually pretty expensive to do, and there's been great strides. You see them with HBM being used in the AMD GPUs. NVIDIA's announced they're going to put in their GPUs. There are some processors doing HBM. It's all predicated on those TSVs not being, you're willing to tolerate that cost, but also that DRAM has equivalent read and write latencies. The fact is that the underlying physics, the DRAM will not have equal read and write latencies in the coming years. And at that point, there are some memory guys already looking at co-packaging Gen Z with DRAM for that. So it gets rid of the TSV cost and sets them up for the future where you have unequal latencies between read and writes. So you never sacrifice performance then. And the way we've designed the point-to-point protocol, we're about 80% protocol efficient, and we can actually scale in the co-package up to, say, 256 or so lanes for reads and writes. So you can actually, we also have asymmetric support, so you can have more on reads, but you can actually stage in this. I hate these things. You can tell I do a lot of work with microphones. You can actually put in tremendous bandwidth. So 256 wide is about what you get, and you can have multiple of those paths when you have HBM. Typically HBM today is 8 120-bit wide solutions. We can definitely accommodate that. And we eliminate the TSV cost, which is huge. If you look at the size of the DRAM next to it, it's a huge. It's like, That's the TSV, and here's the DRAM sitting next to it, right? It's a huge implication in there. So nothing wrong with TSVs, it's a price, and some people don't want to pay it long term. Yeah.
Is it possible to spread Gen Z infrastructure between data centers using kind of PVDM bridge?
I did not design the protocol to do disaster configs. So at that point, I would recommend you just flip to a Metro Ethernet gateway. Now you can create Ethernet gateways here fairly trivially, because if you've got the ENIC coming in and you're doing everything as though it's a real Ethernet NIC, you can come in and hit, and all it is change the framing that you've done. You've got everything there, and you just bring together the packets into a single Ethernet frame and you put it out. Similarly, when an Ethernet frame comes in, it gets segmented and redirected to the appropriate node. So you can actually support large send offload, receive side scaling, all those things that you can do with Ethernet, you can do with Gen Z in the simulated NIC. So I would just put it into the gateway and let the gateway push it out onto the native Ethernet. Okay? Yeah?
Before I was able to photograph the, I guess I can look this up.
Sure. Where do you want to go?
It was the members,
Oh, really far back.
Yeah, really far back.
I know the question you're going to ask.
Yeah.
This guy from Santa Clara is not there.
Yeah.
Is that your question?
Yeah. He's not there. I don't see it. We're still alive.
Yeah, the guys in Santa Clara have well aware of it. They've chosen at this time not to do it. They have their own technologies they're pursuing. They're definitely invited to attend and participate. I will say, though, that particular companies, their architects in that, within various forms when it came to mechanicals, doing some stuff at the connector level, doing stuff in PCI Express, et cetera, to enable all of this stuff, have been extremely accommodating. They've been great partners. They've been good industry members. They've just chosen at this time to kind of do their own thing on certain areas. So I think, people always raise that question, but one of the things I point out to people is because that particular company isn't there, you actually have an opportunity to really innovate now because they're not dictating terms. And so there's an opportunity to really do something different. Yeah?
When is process code coming from the other guys? The guys from Sunnyvale, for example.
Like I said, it's going to be coherently attached in 2020, and then native is post-2020, and I can't go into their...
So you do have process support in 2020 is what you're saying. And
Yes.
I want to also understand software model. Is it a PCA software model, or are we talking about something new?
Whatever you want to do. If you're doing memory, it's however you access memory. If you're doing PCI, it's PCI. So it supports everything we try to do is very software defined. So you can set up any topology, any routing algorithms. It just comes down to what you want to innovate inside the hardware.
Should we more look at it as a stitching system as opposed to
A stitching system?
a switching system? Something like Ethernet, for example.
So we support point-to-point. We have optimizations to do really good point-to-point communication, and you can mesh. And if you're trying to do things like coherency, or you're trying to combine coherent, non-coherent simultaneously across Gen Z, because Gen Z does have a coherency capability, you really don't want to do switches. So this is where you see more people do meshes because they eliminate the switch hop. The problem is once you get to a mesh, like there's one GPU vendor who does 32 GPUs. You actually have to hop through GPUs to make that work. I contend that the cost to hop through an intermediate node or two is more than the cost of putting in one switch. So this is where our very low latency switch latency really comes in, because now you do a certain amount of scale out, find your next closest 4 to 8 friends, works great. You say, hey, but I really want to do 16 or 32 or 64 or whatever, put a single switch in there, okay?
From what you're saying, it doesn't look like you're completely dependent on the processor, because you can do a PCIe bridge-based model. Is that right? Or like
If you want to do load store, you really want to have that coherency point of attach. If you want to just do I/O and block and things like that, sure, you could do it with a PCIe attach. Again, the problem you run into is there's a latency to pay, right?
Yeah.
And it'll be similar to what happened when we first did PCI Express years ago. We had an I/O hub sitting on the coherency bus, and that's the kind of the same role that Gen Z bridge would be in. And eventually you pull it into the processor. I just don't think it's going to take as long as it took with PCIe to get stuff integrated, because Moore's law is our friend. There's a lot of stuff we can do now that we couldn't do before, and it's just a matter of intercepting those processor design cycles.
Thank you.
Any other questions? I know I'm going fast, but
400, 100, optical.
so we support co-packages, obviously, typically silicon interposer or something. You can do copper within the enclosure, FR4 trace. You can do internal cables with copper. You can do photonics. We actually define a physical layer abstraction. So one of the things that PCIe did is the guys in Santa Clara created what's called the pipe spec. And that's pretty much what everybody did, but they still own that spec. We actually said, let's create an open abstraction for that to work. And as a result, the upper level logic is completely phi agnostic. So you can substitute in copper, silicon interposers, photonics, you name it, over time, and 90-some% of that logic is completely reused. It's only at the PLA, the physical layer abstraction, to the phi, do you substitute something in.
You still have problems with getting the receivers.
Silicon photonics is 22 timeframe for some stuff going on. There's been a lot of advancements in there, especially with modulators.
Well, IBM knows everything there is to know about silicon photonics.
I would disagree with that.
Yeah, they're not in the business anymore. They could not.
So my company in particular has a bunch of silicon photonics research. It is funded in part by the government, so a lot of it's public. And you can see the ring modulators that are going on. They've got 16 lambda already working. They're working on 64 lambda type solutions. So eventually, we should be able to have 22, 23 time frame, basically terabyte a second type links.
Let's hope so.
The other thing we're trying to do is, if I say FEC, forward error correcting, you guys understand that? We try to stay FEC free, which means we don't incur the FEC latency, which is about 100 nanoseconds per hop. And we do this through a combination of multi-CRC capability, both in the packet protocol as well as the FLIT level. We have DFE burst protection in. We've got 8-bit burst protection itself, 100% lane fault isolation, 4-bit type randoms that can occur due to DFE and such. So we actually have very strong data integrity. Our mean time to false packet acceptance is 10 to the 20th or something years. I'm not an info theory expert, but it's extremely good. So we actually believe we can run FEC-free within an enclosure, within a rack. We'll have to see if we can run much longer distances. It'll come down to, if you're doing multi-rack scale, how good your photonic subsystem is and your switching.
And how low cost?
The ring modulator type approach is incredibly low cost compared to the stuff that's been done in other technologies. Yeah, sorry, Pankaj.
So, JDEC, you guys had put up Gen Z as a
Yep.
proposal. What is, I do not know what the status of it is.
It's JEDEC confidential, so I can't tell you in public here.
Okay.
But yeah, we proposed it. We actually originally didn't want to do that in JEDEC, but there was an alternative put forward
You
in
have to get a
JEDEC.
release of the JEDEC, Chairman.
Members can talk.
Not really.
If they're on the same task groups, they can.
Come down and
Anyway, yes, we proposed it into that form as well. Any other questions? I think I'm probably near my time. 2 minutes.
Mike, can you clarify a little bit about your comments on processing the memory? Because Gen Z is basically a load store protocol. And the other thing that you said it might have is some support for carrying a transport on which you could route a coherence mechanism if you chose to.
Mm-hmm.
How do you, are you a little bit reaching when you're saying that any function could be on the other side of
No.
the wire? What are
No.
you really saying?
So there's a couple ways to do it. So there's kind of transparent accelerators and non-transparent accelerators. A transparent accelerator might be that when I read or write to a particular address, actions get taken by the media controller. So for example, encrypt, decrypt, compression, et cetera, could all be inline and completely transparent to the requester, the processor, for example, on the other side. You could also have it to where coherency operations. For example, if you're coordinating something between an accelerator that's not visible to the processor, you could have it to where the accelerator takes a cache line private, and when the software says, hey, we're going to update something, it causes an invalidate to occur. When that occurs, that's a signal to the accelerator that work has happened on the page that you're accelerating. So you can do that transparently. And then in the non-transparent model, you do more like a traditional work queue model, which is kind of what NVMe does. So you can actually make this stuff transparent, seamless to integrate, or visible. And it comes down to, at that point, there's lots of things you can do at that level, because the coordination is what matters, not the contents and the operation you do. Now, the other thing to keep in mind is you have to have, and this is where our media abstraction comes in, you have to be able to tolerate a certain amount of latency. So we actually communicate worst case latencies and such. So if you are doing an encrypt, decrypt, et cetera, the processor won't time out thinking something bad has happened. It simply says, I know this is asynchronous in its operation, it'll take a little longer. And most people don't realize even DDR is variable. It varies from about 50 nanoseconds to 170 nanoseconds. So you can do a lot of work in there that you couldn't do in other technologies to do value. Okay, so I think I'm out of time. Any last question? Okay, thank you.